Good morning, everyone. We're going to continue along in Chapter 6. I think we're going to, for the most part, finish Chapter 6 up today so that we can then move on to Chapter 7 on Wednesday. We only covered the first 4 sections out of Chapter 7. We won't return to the remaining sections in Chapter 7, so we'll pick up in Chapter 8 after Midterm 3. So our stopping point for coverage for Midterm 3 next week will be Section 7.4. And I think we'll roughly be through that section after Wednesday's lecture, and we'll have most of Friday to review and next Monday as well. So hopefully we're into review and looking back at that one little section out of Chapter 5 on bond strengths, bond enthalpies, and then into Chapter 6, wrapping that up today, and a small part of Chapter 7. So we're talking about shells or subshells and quantum numbers. Last time, one of the first quantum numbers we were talking about was the n value, where n can start at 1 and then go upward in whole number values. And then L can only be as high as n minus 1, but starting at 0. And then the L value was telling us something about the shape of the orbital. So an s orbital has that spherical shape associated with it. And so the n equals 1 shell is comprised of just the 1s subshell. And then the 1s subshell has only one possible m sub L value of 0, because the range of m sub L's is minus L to plus L. So if L is 0, the only m sub L is 0, meaning there is one 1s orbital, and then we have one orbital possible in that n equals 1, the entire shell. And so then you can also think of the number of electrons that are possible in the shell, because I can get 2 electrons per orbital. So this will be 2 times 1, or just equal to 2. So I have 1 orbital, 2 electrons each, for 2 total electrons can occupy the n equals 1 shell. And so this is why our first row, hydrogen, helium, are 1s1, 1s2 configurations. So these quantum numbers will be directly linked to configurations, and that's directly linked to the information that we can see and the way nature kind of sorted itself out onto the periodic table. So then we have the n equals 2 shell, and so that's comprised of the L0, the L1, and so that's going to be the 2s and the 2p subshells. And so these are our subshells. We have a 2s subshell and a 2p subshell. And then the 2s subshell, just like the 1s subshell, just has one orbital possible, because again, we have one m sub L value. The range of m sub L's for the 2p subshell ranges from minus L, so minus 1, 0 to plus 1. So we have 3 different m sub L values telling us we have 3 2p orbitals. So that tells us we can get 2 electrons into each of those orbitals. So if we're thinking the electrons into these orbitals, or into these subshells, we're going to get 2 plus 6 for 8 total electrons that can occupy the n equals 2 shell. And so our second row, 8 across, we're filling into the 2s and the 2p subshells. Now when we get to n equals 3, we have a slight complication with the periodic table and where we're going to squeeze these 3D subshells in, but we'll see that in a minute. But we have our L equals 0, L equals 1, L equals 2 subshells. So we have the 3s, the 3p, and the 3d subshells. And remember, the p here means we have a p-shaped orbital. The d shape means we have kind of a cloverleaf-shaped orbital. We have 2 sets of lobes for the d, 1 set of lobes for the p orbitals. And so the L value is telling us about the shape of the orbital. And then the number of m sub L values, the range of m sub L's for the L minus L to plus L. So we have 3 values for the 3 orbitals possible for the 3p subshell, but we have 5 orbitals possible for the 3d subshell. So we have 5 3d orbitals, 3 3p orbitals, 1 3s orbital. And so that's giving us, in terms of electron counts, a total of 18 electrons. Now, the third row deviates from the n equals 3 shell because we don't fit the 3d orbitals yet into the third row of the periodic table. So we have to get across the 3s, the 3p, and then calcium, potassium and calcium are going to fill into their 4s subshells. And so we're going to fill into this 4s subshell next, and then ultimately come back to fill in the 3d subshell afterwards. You can see this by nature because we have 10 elements across after we get across the 4s subshell. And so our fourth row of the periodic table, if you count 2 plus 10 plus 6, ends up being 18 elements across. And so our n equals 4 shell ends up being comprised of the 4s, then the 4p. So we'd fill into the 4p subshell once we get across zinc, back into gallium, germanium, arsenic, selenium. Those elements are filling into the 4p subshell. And so we have 3 4p orbitals, 5 4d orbitals, and then we get up to 7 4f orbitals because, again, the L value of 3, we go L value is 3, so we go from -3 to -2 to -1 to 0 to 1 to 2 to 3. So that's 7 different values. So I can fit 7 electrons into the 4f subshell. And so the F subshell is the lanthanide and actinide series. So those are the elements that are last filling their electrons into an F subshell. And so the number of electrons possible here, 2 for the 4s, 6 for the 4p, 10 for the 4d, 14 for the 4f. And we could continue, but at this point here, let's just take a stop and try to figure out kind of how the periodic table is going to help us figure out the order that these subshells are filled into with electrons. Okay, let's look also at a few questions. So this question here, how many electrons at most can occupy the n equals 3 shell? So if this was a test question, what we're thinking here, the n equals 3 shell should be comprised of what? The L equals 0, the L equals 1, and the L equals 2 subshells. So the 3s, 3p, and the 3d. We haven't done a quiz in a while, so why don't we go ahead and take a look at the quiz. I actually forget the name or the password for it. So the password for the quiz is light. If you want to do this as question 1, and then there's a question if you want to take a moment or two to talk about the test, if you want to leave any feedback. So I'll give you guys about 2 or 3 minutes. So if you want to answer this question, think about how many electrons can occupy the n equals 3 shell. And then if you want to leave any exam feedback about midterm 2, feel free. All right, so let's talk about the question here. So we end up with 1 3s subshell, 3 3p subshells, and then 5 3d subshells. We'll review Hund's role in a minute, but when we're filling into these subshells, we're going to see that we're going to try to maximize the spin of electrons, and we can pair the spins with more electrons. So we can try to maximize the spin into the d subshell and then pair those up with a maximum of 2 electrons into each orbital. So that's the picture of how we're getting 2 electrons into the 3s, 6 into the 3p, 10 into the 3d for a total of 18. Most of the class was on the right track. We kind of answered it on the previous slide anyway. So that's 18 electrons that can occupy the n equals 3 shell. And so let's take a time out for a moment to talk about midterm 2. Overall, the exam scores were about the average 68 to a 69% for our class. We actually were the highest of all the sections. So I think that's a great job by the class as a whole. I think if you look at midterm 1, I think we did pretty good midterm 1 compared to the other sections too. We're like 71, 72%-ish on that exam. Some of the other sections had dropped like 10% or so. And if you recall, I had said after midterm 1 that midterm 2 topics are trickier, that scores could go down, but it's just a matter of trying to do our best. And I think we did a great job preparing for midterm 2. Now, something I think kind of everybody can take a glance at is how they did on both midterms 1 and midterm 2. One thing I kind of recommend is for the students who happen to be in that 75% plus range on both exams is to not stress too much. So I know sometimes students score, if you've gotten 78 and 82%, I think those are great scores. I don't think you need to beat yourself up if you're getting scores in that range there. So that's the first thing, is kind of think about how you did in the 2 exams. If you're doing well but not perfect, don't beat yourself up for not getting hundreds. It's hard to get 100% on any kind of test like this. Second thing I'd say is if you did better on midterm 2, a lot of students did better on midterm 2 than they did midterm 1. Certainly know that you're doing things probably in a better way than we prepared for midterm 1. Some students did drop on midterm 2, but I think midterm 2 was trickier, so I don't necessarily think, again, we need to beat ourselves up. If you went from, say, like a 90 to an 80, both those scores are good, so don't beat yourself up for that. If we're dropping by like 5 or 10%, the test did get a little bit harder. So I just think the question becomes, how do we fine tune some of our study habits? And then if either one of the scores, or more recently the midterm 2 score, was kind of in that below like 40% range, that's just where we need to think about what are the best kind of ways to prepare for a given class. I think every individual student could be a little bit different in this regard in terms of, do we need to read more? Do we need to rewatch lecture videos more? Do we need to watch the alternate lectures? Feel free to come to office hours as much as you want. Office hour attendance is pretty good, but for those who have been kind of on the fence of coming in, come in. You can ask whatever questions you have about the class and hopefully improve your knowledge through coming into office hours. And so the other thing is, I think, just getting good at the sort of task of trying to learn a concept, an idea. That's where those practice exercises come into play. That's kind of where the homework assignments that are due on Carmen come into play. Those are meant to be simple problems that are helping you try to understand the content, apply it, and just really just have simple problems that we can understand, all the ins and outs of those problems. And if we're doing that, I think when we look at the practice quizzes, we can practice the material we know and hopefully get good scores. So like one recommendation I have is, if you're doing like a daily quiz and you have to refer to your notes a lot, even if you get the questions right, just know we got to get rid of the notes. Like, we have to learn the content so that we don't need the notes to help us through the problems. So try to take your quizzes, your practice exams, closed book, closed note. Otherwise, we're just going to be really relying on that extra help when we get to the exam. It sounds silly, but sometimes if we're always double checking something in a book, when we get to a test, we'll get really anxious because we can't double check anything, and that'll just like sometimes turn us into a tailspin. So I say just get a lot more practice recalling information on your own. That'll help you learn the material better and hopefully help improve those exam scores. Now, midterm 3 is only over like one whole chapter and part of 2 others, so I think small set of material, hopefully we don't have to study as much material, so hopefully that allows us to fine-tune those chapters. So hopefully we have a chance to rebound by just having a smaller set of coverage for a test. So we're not trying to study 3 chapters, we're just trying to study, well, it is parts of 3, but it is some small parts of 2 chapters and that all of chapter 6. Another detail to mention is that, think about your lab score, your homework score, and your recitation score, because these in total are 40% of the class. All the exams in total are 60% of the class. So it's not like you need to light the class on fire with the exams. I mean, there's a little bit of a cushion you can get if you're getting good lab, homework, recitation scores. These here tend to average in about the 90% plus range. So if you're getting 90% plus of the points in the lab recitation homework part of the class, you don't need to pull that exam score to get a final score into that range. Or if you're just hoping to get out of the class with like a B or a B plus, have a little bit of a cushion if you're getting scores that are in that 90% plus range on your homework and on your labs. So just know that hopefully we're getting most of those points, so they give you a little bit of a cushion. So you might think of just how these scores kind of like go together and give you a little bit of a cushion. So again, hopefully we can get scores as high as we can get them. I don't think anybody's compelled to get a low score on any of our exams. I don't think we're writing our tests to be hard, to try to get scores low. We're really trying to write questions we hope everybody can answer and have a good shot at getting into that 80% or that 75 or so plus range. So I'd say on your practice test, shoot for a little bit higher than you want to get on the real exam. But if you're getting 75% plus of the points and most of the homework and lab points, your final score is going to be in that B or better range. So I'd say, hopefully midterms 3, 4, hopefully those exams, by the nature of midterm 3 being a little shorter content, midterm 4 would be mostly conceptual, not a lot of math. Hopefully this gives us a chance to kind of catch up and sort of see where we get. Okay, so kind of all the comments I wanted to have about the exam. So let's take a look at this question here together. So we have an electron in a 3p subshell. What is its range of m sub L values? And so when we have a 3p, it's just kind of recognizing that the n, I wrote m, not the right n. So the n value is 3. That's what this means. Now, sometimes we get a little confused in that when n is 3, L can be 0, 1, or 2. But when we have a 3p subshell, this is precisely the L equals 1 subshell. So when we see the p symbol, that means L's 1, S is L0, P is L2. Let me start this over again. So let me write out a range of L values real quick. 0, 1, 2, and 3. And the 0 corresponds to S shape, 1 corresponds to P shape, 2 corresponds to D shape, and then 3 corresponds to F shape. And so then the number of lobes, if you will, we get 0 for the S, 1 set of lobes for the P, 2 set of lobes for the D, 3 sets of lobes for the F orbitals. If you go back to the shapes, you get the sort of basic kind of infinity shape for the P, you get the cloverleaf shape for the D, and then you get this kind of triple set of lobes for the F shape as the basic shape for those types of orbitals. So again, no lobes for the S. And so then when we have a 3p subshell, L can be 1. Then the range of m sub L is that L value negative through 0 to plus 1. And then any integers between, and of course there's no other integers between negative 1 and 0 and plus 1. So we just have 3 values. So we have a range of 3 m sub L values. So the range of m sub L's for the subshell would be -1, 0, and 1. And then each of the electrons, so the range of those values is telling us we have 3 3p orbitals. And then the m sub s value is what is given here. The m sub s of each electron in each of those m sub L values could either be +0.5 or -0.5. So we can have 2 electrons in each subshell 2 electrons in each orbital maximally. Now let's talk about what these orbitals kind of look like in terms of a probability distribution. So if we got into this topic from the idea that electrons aren't really discrete particles where, an electron's not going to orbit the nucleus with one radius, it's going to orbit the nucleus or spin around the nucleus with some probability distribution. And so the way you can sort of map out the probability, if you're looking at the nucleus and where the electron is, you can sort of think, well, the probability, you can think of the radius of the atom. Where's the probability that you're going to find the electron? Probably pretty close to the nucleus for a 1s subshell. And so then if you compare that to a 2s subshell, the probability of where you're going to find the electron, because the orbital is bigger, then the probability is going to be further away from the nucleus. If we then have a 3s sort of subshell, the probability is even further away. But we end up having these things called nodes. Nodes are regions of no probability of finding an electron. So the 2s subshell has 1 such node. The 3s subshell has 2 such nodes. So we have 1 node for the 2s. We have 2 nodes for the 3s. So we have two of these regions of 0 probability for the 3s. If we had a 4s subshell, it'd be even further from the nucleus, so we can predict the 4s subshell should look something like this. So we're going to have 1, 2, 3 nodes. And now, there's one little application in Chapter 7 where it might be useful to know that you have a probability, even for a 2s electron, there's still some probability that that electron is relatively close to the nucleus. I think that's the main takeaway here, is that even as an orbital is increasing in size, that there's still some probability that the electron's relatively close to the nucleus. And we'll see how that plays out. We'll see this come up again when we get into a topic in Chapter 7. And so hopefully this will help us understand something when we get to Chapter 7. And so that's what sort of the probability distributions look like for functions. You can compare probability distributions for S versus the P functions. The only odd thing here is this is for what you call a hydrogen-like atom. So you're picturing a single electron atom. So there's no other electrons other than one electron, and you're comparing what the orbitals look like for S versus P functions. And the reason why I bring this up is it appears that the P subshell is closer to the nucleus than the S subshell, and that's only for the case where you just have one electron. So as we start to think of the relative size of orbitals, if I'm thinking of like a carbon atom, so if I'm picturing carbon instead of hydrogen, I'm picturing carbon as a 1s2, 2s2, 2p2 configuration. So I'm picturing an atom that's using a 1s subshell, a 2s subshell, and then a 2p subshell. And I like to think that the 2p subshell, because you have a 2s subshell in the way, is going to be larger on average than the 2s subshell. And so this diagram might confuse you a little bit, but it's for a single electron atom of hydrogen, or a hydrogen-like atom with its electron at a 2p subshell instead of the 1s. And then the idea, though, is the 2p subshell is larger than the 1s. The 2s subshell, you can kind of see, again, that nodal plane. One thing with the 2p to notice is it doesn't have any of those nodes, kind of like the 1s does, so there's no nodes for the 2p. If you move to the 3p, then you pick up having a node. It's maybe a little bit hard to see here, but the 3p subshell does have one node. So there's a subshell here that is our 3p, and there's one, what we call radial node, one node on the radius of the atom. So the nodes on the previous slide, so the 2s had one node, that was a radial node, and then we see here the 3p has one radial node. Not a big detail, but again, it's just kind of showing you that even a relatively large 3p orbital still has some probability of the electron being relatively close to the nucleus. And so these radial distribution diagrams are just trying to show you kind of that orbitals are pretty diffuse in terms of they're pretty spread out. They're not really centered on the atom, but they're pretty spread out in terms of the space that they're occupying. Okay, now, sometimes these are exam questions. These are my least favorite exam questions because it just kind of becomes, wait, we're just supposed to memorize this. You might see practice exam questions on this topic. I just want to make sure we see where they're coming from. So how many radial nodes does the radial probability distribution function? So we call the distribution functions we were just looking at radial probability distribution functions. And so if we're looking at the distribution for the 6s subshell, we just kind of come back to the 1s subshell in terms of radial nodes had 0. The 2s had 1, the 3s has 2, the 4s, we pointed out, has 3. So the 5s, of course, will have 4, and then the 6s will have 5. So we're going to have 5 of those radial nodes for a 6s orbital. I've never liked this question because I've always been like, okay, so what? What difference does it make how many radial nodes it has? It's just kind of a cute little exam question that you might see asked on some of our old practice exams. And then one other thing to mention is, well, what's the difference between these radial nodes and the node in like a p orbital? So we mentioned before that there's this like planar node, or there's this node through like the sort of center of the atom. This is what we would call like a planar node. And this is just going to be equal to the L value. So like if you have a p orbital, it's going to have one planar node. And if you have like a d orbital, so if we picture having a d orbital, say here, that you have one planar node here and another planar node here. So a d orbital has an L of 2, and it has 2 planar nodes. So we also see nodes. Nodes are just regions of no probability of finding an electron. So we have planes of no probability, so planar nodes for the basic shapes of orbitals. And then we have radial nodes for nodes along the radius of the atoms. And one thing to go back to, if we think back to the 2s subshell for a minute, like what this would look like is, since you have nodes along the radius of the atom, it would just kind of look like you have an inner sphere and then you have like an outer sphere. And then there's just a region of no probability between those 2 spheres. And if we could shade this really neatly, you would just see a sphere that's shaded kind of in the middle of the sphere highest, and then the center less, and the outward less. And then the same thing, you'd have a second sphere where the shading would be more in the middle than it is in the outer part of the sphere. So if you can also picture this on the radius of the atom, you would just have a greater shading in the middle and a less on the outside. Then you'd have a greater shading in the middle and less on the outside. So just trying to picture like spheres in 2-dimensional form with a graph with the radial distribution function versus picturing an actual spherical orbital for like an s orbital. So then how many radial nodes does the 2p orbital contain? So the 2p, we pointed this out on the slide, had 0. So the first time you can have an s orbital is 1s, so no radial nodes. The first time you can have the first n value that has a p orbital is the 2p, so that would have 0. So the 2p orbital would have 0 radial nodes, but then 1 planar node. And that 1 planar node is what makes it the p orbital. That's that node through the center that makes it have that lobe appearance. So that planar node is the one through the center of the atom. So, weird topic. You might see some practice exam questions on it. Not sure we'll see it on the real exam or not. But if you see it on the real exam, really basic question, but it's kind of, like I said, when you identify the 6s has 5 radial nodes, I'm not sure what that really is supposed to mean, but it's just a number that you can answer when asked a question like that. So let's get back to the periodic table. Let's get back to thinking about hydrogen versus helium versus like lithium. We were talking about this on Friday, but we have hydrogen has a 1s1 configuration, helium a 1s2. So 1 or 2 electrons are going into the lowest energy sort of subshell that we have, the 1s subshell. And then the next subshell that we fill into is the 2s, so we go 1s2, 2s1 for lithium. We saw that beryllium would just be a 1s2, 2s2. We're going to see that the lithium, beryllium, sodium, magnesium, potassium, calcium, those elements are always last filling their electrons into an s block, into an s subshell. We're going to then see that if you get across the boron, carbon, nitrogen, and those elements, and then all the groups downward, those elements are last filling their electrons into a p subshell. That's why they're sort of grouped by elements of 6. And so when we get across from beryllium being a 1s2, 2s2, to boron being 1s2, 2s2, 2p1, so we've put 1 electron into the 2p subshell where there's 3 different orbitals. It doesn't matter which one we choose, we're just putting 1 electron into any one of the p subshells. But then for carbon, we're going to follow Hund's rule, which says when we're filling into equal energy orbitals, that's a fancy word for that is degenerate orbitals, we maximize the spin of the electrons. So we put the electrons into 2 different orbitals and pair their spins together in the same direction. And so when filling degenerate orbitals, the lowest energy is attained when the number of electrons having the same spin is maximized. And so that just means for carbon, we're filling into that 1s, 2s, 2p orbital. And then let's use a second 2p orbital. Instead of putting 2 electrons into 1 orbital, where they're going to be closer together, let's spread them out. So Hund's rule is just allowing electrons, when possible, to spread themselves out into different orbitals. Nitrogen can do this with all 3 of the p orbitals with 1 electron. So that's our 2p3 configuration for nitrogen. If we get all the way across to neon spin pairs, we pointed this out. This is kind of the thing when we were ending class last time, was pointing out that neon caps off the 2p subshell with 6 electrons. And then sort of would take a lot more energy to put electrons into a 3s subshell. It's going to be hard to remove electrons off this atom once it's filled that subshell. So neon ends up being a perfectly stable atom. Same thing with helium. So filling off a subshell allows an atom to attain a stability that other atoms are going to have to get to by sharing electrons or donating or giving up electrons. Now sodium just then puts an electron into a 1s, into the next s subshell. So sodium goes into a 3s1 for its last electron. And then we can start to write condensed configurations. Like we can write sodium's configuration as that of neon followed by a 3s1. And if you get to, like, even if you're looking at like rubidium, rubidium is element number 36. You can write rubidium configuration as the preceding noble gas krypton. And then the only thing you might want to remember is you might know it's an S1 because it's going to put its next electron into an S subshell, but you can just count downward. Hydrogen's a 1s, lithium's a 2s, sodium's a 3s, potassium's a 4s, so rubidium would be a 5s. So this would be a 5s1. Now, we'll go back through the elements in between, sodium and rubidium, but we can determine something like rubidium's configuration pretty straightforwardly.
Do you know from nitrogen to oxygen? Does it matter which oxygen we filled up next?
No, so like if we go to like oxygen, good question. So when we need to spin pair, it doesn't matter where you're going to spin pair. So for oxygen, if you're going 1s2, 2s2, 2p4, and we're filling into a diagram for our 1s spin paired, our 2s spin paired, and then 1, 2, 3, and then 4. Like we'll almost always do it from left to right, but you can spin pair either of them and it's the same. And so we're just spin pairing one of the Ds. In fact, like it's not like wrong necessarily to write them all up versus down. Like we could have written nitrogen with all these pointing down, and that technically is perfectly legal too. So there's nothing wrong with writing nitrogens this way. Like that's not wrong. It's just more traditional. We'll write them usually net up. The thing that would be wrong would be these things. So if we went like this, why is that wrong? Some students say, well, that doesn't follow Hund's rule, but that violates Pauli exclusion principle. So this is a Pauli exclusion principle violation because we'd be portraying two electrons that would both be spin up in an orbit. So those electrons would share the same set of 4 quantum numbers. So that would be a Pauli exclusion principle violation. You could probably say it violates Hund's rule too. That's not what Hund's rule says to do. So then what's wrong with this one? That configuration for nitrogen would be wrong because we didn't maximize the spin, so that would be a Hund's rule violation. So this one would be wrong for Hund's rule. So again, we want to put them all into the same direction, maximize their spin. So then the order which we fill electrons, either we can sort of picture diagrams like this, where you can maybe get a sense that the 1s, the 2s, the 2p, we've gotten through the 3s. You can probably imagine the 3p comes next just because there's 6 groups of elements that come after the 3s block. And then you can probably get the 4s comes next because, again, there's an s block of 2 elements before we get to the next group of elements. And then what comes after the 4s? Well, again, we're looking at the periodic table. We're looking scandium to zinc as the next elements, 10 across. Those are filling into a D block. Then where are the next elements? Gallium across the krypton, 6 elements across. That has to be the 4p. And what do you think then comes after the 4p subshell? It's what we're filling in with rubidium, would be the 5s. What comes after the 5s? We have the D block. So we'd have the next D block. So our first D block was a 3D, so this has to be a 4D. And then we come to the next P block, the 5P. Now, a few things. One, I'll show you a different periodic table that'll hopefully reiterate the counting. If we look at the periodic table, we can almost just look at it, mark it up, and hopefully get the right number for the S versus the P versus the D. But the second thing, or one thing I want us to see before we move off the slide, is if you go back to the Bohr model, where we went from n equals 1 to 2 to 3 to 4 to 5. As we go to low energy, there's a big difference between n equals 1 and 2. As we get to the third, fourth, fifth n values, those energies start to kind of become a little bit closer together. And so if we have in the back of our mind that these energies are starting to sort of compress themselves together, we're going to then probably understand towards the end of the chapter why some configurations are anomalous or have anomalies. So we're going to see that when we get into the D block and the F block, that there's going to be some switching of configurations. We're going to see that we don't always get the configuration we might expect. Okay, so let's look at titanium. So titanium element number 22. So you can find that in the transition metal block, the first transition metal row. And so then what's the ground state electron configuration? Well, if we go from scratch, and this is really almost like looking at the periodic table. It's like I'm filling hydrogen to helium, then lithium, beryllium, across the P block. Then I go to the 3s2, 3p6. Then I come to potassium and calcium for a 4s2. And then titanium's 2 across into a D subshell. So it's going to be 3d2. Now, a few things. One, how do I know this is a 3D? Why is this 3D and not 4D? Well, you have to kind of think the first time you can have an L of 2 is when n is 3. So the first time we can have a 3D subshell is that 3D subshell. It's just the way the periodic table is put together. It's just these elements weren't able to fit themselves into the n equals 3 row. They had to sort of wait for the fourth row of the periodic table. So 3D, even though it's in the fourth row of the periodic table, and that's the first time we can have the D subshell. Just like the first time we can have an L of 1 is when n is 2. So the reason why we don't have a 1p subshell is because that's not possible. It's not possible to have a 1p subshell. And so the highest L can be is n minus 1. Okay, so how many unpaired electrons does this atom have? Unpaired electrons is really asking us to apply Hund's rule. So it's really saying apply Hund's rule to putting these electrons into these subshells. Now we could do this. We'll see we don't really have to spend a whole lot of time when you have a filled subshell. And we can really gravitate ourselves to that unfilled subshell. So this is our 3D. So we have a 1s2, 2s2, 2p6, 3s2, 3p6. So if you have a filled subshell, all the electrons are spin paired. So you have a filled 4s2, those electrons have to be spin paired. It's the 2 in the D subshell where I have 5 d orbitals. So I have 5 orbitals to put 2 electrons in, so I maximize their spin, put them both in the direction upward or downward, but so that they're pointing in the same direction. So I have 2 unpaired electrons. Now, let's talk about valence electrons for a minute. So let's also then take a step back on valence electrons. So let's go back to carbon for a minute. So if I go to carbon is a 1s2, 2s2, 2p2, carbon has 4 valence electrons. And so the valence count we're going to see is either one of two things. It's either going to be the outermost shell. So the outermost shell would include the 2s2 and the 2p2. So the valence electrons are those in the outermost shell. So not outermost subshell, but outermost shell. So the outermost shell will be n equals 2, so we have 4 n equals 2 electrons. Now what do I do for titanium when titanium's kind of filling into 2 subshells simultaneously? It's filling into the S subshell and it hasn't completed the 3D subshell. So what we're going to do is count the valence electrons as the outermost shell plus any electrons in a lower but unfilled subshell. So we want to count the outermost shell. So the outermost shell would be 4, because that's the outermost n value for all the electrons in titanium is that 4s2. So I'm going to at least have those 2 electrons as part of the valence. Then I want to add these 2 electrons in too, because they're part of an unfilled but lower n value subshell. So I come up with a total of 4 valence electrons for titanium. Now, why this matters is that these are the electrons that are going to participate in bonding. These are the electrons that can be lost to make cations. These are the really important ones for us to focus our attention on as we get into bonding in Chapter 8. So identifying valence electrons is like identifying the electrons that are going to maybe overlap with each other to make covalent bonds, or the ones that might be shared or lost to make ions. And so we want to be able to identify the outermost shell, and then we also want to count any electrons in a lower but unfilled subshell. Now this gets a little bit tricky in a way. Let's think about zinc for a minute. So if you go to zinc, zinc has an argon configuration. So argon's configuration all spin paired through argon. Then we go 4s2, and then 3d10. Now, the way I would look at this is now filled. So this isn't an unfilled, this is a filled but lower subshell. And so now zinc would only have 2 valence electrons. And then zinc actually only forms a +2 cation, so this kind of makes sense for a property of zinc. You'll see that cations like titanium, vanadium, chromium, manganese, these form multiple different cations. They'll form +2, +3, +4 cations commonly. Zinc only forms a +2. It doesn't form any higher because those d subshell electrons are going to be really hard to remove once that's filled. So we have 2 valence electrons for zinc and then 0 unpaired. So just because we have valence electrons doesn't mean they're unpaired. So we would have 2 electrons in the 4s, and then we'd have in the d, where there's 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all spin paired.
So does that make it true for all 3d10 electrons that they would all have 2 valence electrons because the d shell is completely full?
Yeah, kind of. It gets a little nuanced. Like copper's a weird one. Copper has an anomaly, something we'll talk about later, where its configuration turns out to be a 4s1 3d10. So that's a complicated question. How many valence electrons does copper have? I'm never going to put that on a test because it probably would be 1, maybe 2, maybe 11. Like it's really hard to come up with some on the very fringe of the periodic table. But zinc's is pretty easy. If you get to like gallium, one important thing is if you look at carbon, for example, the entire row of carbon, so carbon, silicon, germanium, tin, lead, those all share having 4 valence electrons. So let's look at germanium. So germanium would just fill into the so argon, 4s2, 3d10, and then 4p2. So this looks a lot like carbon, where it has a 2s2, 2p2 for carbon. So this is the outermost shell, the highest n values, the highest shell. And so here's our 4 valence electrons. And that's going to share. So if you can identify carbon has 4, the entire row of carbon has 4. Nitrogen has 5, entire row of nitrogen has 5. So like antimony, bismuth, each of those have 5 valence electrons without even thinking about it. Fluorine has 7 because it's going to be a 2s2, 2p5. So the entire halogen group share having 7 valence electrons. So iodine has 7. Big element, might take you a while to write it out to see it, but you know it has to have 7 valence electrons based on its periodic table placement. So we can also look at a configuration and identify the atom. So if I give you a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, can we identify the atom? Well, one thing we can do is we can just count these up. We're not looking at ions. These are all uncharged atoms, so there's nothing fancy going on with this being an ion. So this is definitely an atom, no charge. We'd say ion if it were an ion. And so we can count the electrons. So I got 18 to here, so I got 18 plus 8. What element does that correspond to? What element has 26 electrons? Iron. So that's just iron. So iron is element number 26, so it has 26 electrons. So an uncharged iron atom, 26 electrons. And so then in terms, like how many valence electrons does it have? How many unpaired electrons does it have? Well, let's focus here. This is all argon. So this here is argon, followed by a 4s2, 3d6. So 4s2, 2 electrons, and then 3d6. So that gives me a total of 4 unpaired electrons, because I have 6d electrons, so net 4 unpaired. And then I have 6 plus 2, I'd have 8 valence electrons. And iron's weird. It's probably the most common ions are plus 2 and plus 3, but occasionally it forms a plus 5. Forms a variety of charge states because it has a lot of valence electrons. Well, let's get through, so let's get past germanium. So we get all the way to krypton, we'll just fill in the 4p subshell. We mentioned rubidium would be the 5s. So getting across strontium in the next transition metal block would be filling into the D block. Let's pick out, let's just do cadmium, the very last transition metal before we look at tin. So cadmium is element number 48, below zinc. So its configuration will be that of krypton, but followed by a 5s2. So after krypton, we come to the 5th row, so 5s2. And then we already filled into the 3D, so the next D block's a 4D, so that's 4D 10 across. So all 10 across. And we could have done it, like yttrium would be 1, zirconium 2, niobium 3. And then all the way across the cadmium for a 10. I'm just saving time by spin up, spin downing them. So these are 0 unpaired, just like zinc, and then 2 valence electrons. Now, when we get to tin directly beneath carbon in that same group should have 4 valence electrons. But for tin, the configuration should be krypton, followed by that 5s2, 4d10, and then back to the 5p for 2. Now, quick question would be, how do you know it's a 5p2 and not a 6p2 or a 4p2? How do you know it's the right number for the p subshell? We'll just go to carbon's at 2p, silicon's at 3p, germanium's into the 4p, tin's into the 5p. So you're just kind of counting downward. And so 5p for 2, and then this is 4 total valence electrons. So our valence diagram could just include the s and the 3p. So we have the 5s and the 5p. Since the 4D are part of the valence, I could leave it off the valence diagram. If you wanted to picture the 4D, there's no reason we couldn't still sketch the 5n, the next 5 all spin paired. So that's our 4D10, then 5s2, and then 5p2. So outermost shell for 4. So n equals 5 is the outermost shell. So I count the 5s2 and the 5p2 electrons into the outermost shell. And then I have 2 net unpaired electrons. So 4 valence electrons, and then 2 unpaired. And so then these are the electrons that are going to be most important for understanding the bonding of something like in tin. Now this diagram here is the one where we can sort of break the periodic table down into the S block elements. So we have the 1s, 2s, 3s, 4s, 5s, 6s, 7s, meaning elements in those blocks are last filling their electrons into the S subshell. We then have the P block elements, which are last putting their elements into the P subshell. So we have the boron group for the 2p, and then downward 3p, 4p, 5p, etc. And we have our first D subshell, it's the 3D. So all we have to kind of remember is the first time you can have a D is when n is 3, L is 2. So that's our 3D. The first time you can have the P is, again, L of 1, so N of 2. So there's not a whole lot of memorization going on here. Just like looking at a periodic table, we can just break the first transition middle row down as a 3D, then the 4D, then 5D, and then the 6D subshells. And then the only last question would be, well, where do we wedge in the F blocks? Well, you have to kind of sometimes follow along the periodic table that you're given here. Like if you notice, it goes cesium, barium, lanthanum, and then cerium down below into the lanthanide series. So every periodic table is a little bit different the way they're trying to show you where the F block is kind of fitting into. Some periodic tables, it's probably more common for lanthanum to be shown down below, and then either one of two things. Either the last element here is listed in the periodic table, or we go 15 across in the bottom and just leave like a gap. Because this is really, the way this diagram is shown here, this is really the way a periodic table should be written and given and put into textbooks. But the problem is it just wouldn't fit. It'd be too small. Or we'd run out of wall space. We'd have to shrink the font down. But in order just to make the periodic table more presentable, what if we just remove the F block and then wedge the table together? Like that's the reason why the F block appears to be kind of goofy on the periodic table, is just a design choice of whoever was constructing one to put on a wall and made this choice of, well, let's just remove the F block so it fits better aesthetically and we can use a larger font size. And so the F block, though, is coming right after the S block. So we go from xenon element 54, would cap off that subshell of that we were just filling into with tin, so that would cap off the 5p2. So then we get down to a 6s2 would come next. So let's do the configuration for something like cerium. So cerium would be a xenon, 6s2, and then we're going to fill into the 4f with 2. So this would be our expected configuration for cerium. And then we would just continue, like praseodymium would put one more, neodymium, et cetera, into that F subshell. So we get all the way across 14, and then we'd be filling into the 5D subshell. So if we were looking at something like, say, tungsten, tungsten would have a configuration of xenon, 6s2, 4f14, and now we're filling into the F block, 1, 2, 3, 4 into the F block, or 4 into the D block. And now, again, how do I know that's a 4F? Because the first time I can have an F is n equals 4. How do I know this is a 5D and not a 4D or a 6D? Because I'm just following along with 3Ds, the titanium group. Its middle group after that is the 4D, and so the tungsten would be filling into the 5D. In terms of a diagram, my valence count gets a little bit kind of goofy for some of these big elements, but I'd have 6 valence electrons here, because that's my outermost shell plus the unfilled subshell. And then my valence diagram, 6s2, and then I'd have 4 unpaired electrons. One too many, so 4 unpaired. So 4 electrons spin unpaired, 6 total in the outermost shell plus the lower unfilled subshell for something like tungsten. And we've been kind of filling into the sort of carbon group. Let's look at lead real quick. So lead would be element number 82. So we'd have xenon. That's 54 my electrons. 6s2, 4f14. We filled all the way across the D subshell. And now I'd be last filling back into the 6p. And again, if I forget it's the 6p2, I'm just coming back to this diagram here that lead's right here. So 2, 3, 4, 5, 6p. So if we count all these up, I get 82. So if you count all the electrons up that have been assigned, we should be able to get to 82, the proper count for lead. So lead would have, like carbon, 4 valence electrons, 2 unpaired, just like carbon, and just like the other atoms in that sort of group. So now the last thing to sort of wrap our minds around, if we look at some of these configurations, they're not exactly what we expected. Most of them are, though. So if we kind of pick up here, nothing before potassium was unexpected. So it's only after potassium, it's only when we get into the D subshell, it's only when those orbitals start to get closer in energy that we were talking about. So potassium and calcium exactly as we expect. And then scandium 3D1, 3D2, 3D3, perfect. And then notice chromium is a 4s1, 3D5. So we didn't create or destroy electrons. We just had an electron from what should have been in an S subshell move into the D subshell. And so what we had was, instead of this that we expected, one of the S electrons moved and was promoted or moved into the D subshell. And so it turns out that there's some configurations that add stability to an atom. Like half-filled subshells, for whatever reason, add a little bit of stability, because we see this kind of continue downward, that molybdenum does kind of the same thing, that having a half-filled S and a half-filled D is where it kind of ended up with its actual configuration. Now, these aren't details you need to memorize. You don't need to memorize which atoms do this. In fact, it turns out not to be periodic. So tungsten didn't do that anomaly. So if you notice, tungsten didn't carry on the anomaly, neither does this goofy. Some of these atoms are, beyond uranium, are not even natural occurring elements. So this would be something like lab synthesized. So then if you go to manganese, exactly as expected, iron as expected, cobalt's expected, nickel's as expected. I mentioned copper earlier has that anomaly. It's a 4s1, 3d10. So going to a completely filled D subshell added some stability to copper. And again, you can maybe comprehend that there's going to be some stability or some configurations that are more stable than others. But here's the kicker. I just want you to be able to give me the expected configuration, follow the rules, tell me what you expect the configuration for an atom to be. Or if I give you a configuration, just count the electrons up and tell me what the atom is. So if I say an atom has this configuration, argon 4s1 3d10, you're just counting 18 plus 1 plus 10, that's element number 29. So you can tell me the atom just by counting the electrons, whether it's expected or anomalous, but don't worry about memorizing the anomalies, because they're also not very periodic. Like copper to silver to gold, that turns out to carry the same trend for those three elements. But then if you look at the nickel trend, nickel is exactly as expected. Palladium moved both s electrons into the d subshell, and then platinum moves one of them and ends at a s1d9 configuration for some silly reason. So there's really not much rhyme or reason. Ruthenium and rhodium do this too, but none of the others above or below do that same anomaly. So the anomalies are very peculiar, and you see some anomalies in the F block. So the F block has some goofy anomalies. So I'll probably point those out at the start of class next time and move off this topic and into chapter 7. Okay, so we'll wrap up here for today. Thank you guys, and have a great day.